Hello, this is Haohua Tang. Today I'll be talking about our paper for ITCS 2024, General Gaussian Noise Mechanism and their optimality for unbiased mean estimation. This is a joint work with Aleksandar Nikolov. First, let us define differential privacy. We say a mechanism M is epsilon delta differentially private if for any neighboring datasets x and x prime being its input, the chance of the output falling in any S only differs up to multiplicative parameter epsilon and additive parameter delta. We would assume epsilon to be a small enough constant such that it is approximately the same with e to the epsilon minus 1. And we consider delta to be a very small lower order term. Another version of differential privacy is rho zero concentrated differential privacy. This is defined by the alpha-Rani divergence. We study unbiased mean estimation in this work. We say a mechanism M answering query F is unbiased if for every dataset X, the expectation of its output equals to the correct answer to F. For our purpose, F would just be the empirical mean mu. A simple example of an unbiased mechanism is just to add any noise with mean 0. Another example would be first do a randomized response, then use post-processing to remove the bias. One might ask, why focusing on unbiased mechanisms? Here are some motivations. First, given some assumptions, there exists a uniformly minimum variance unbiased estimator, that is, the best one over all unbiased estimators. Also, averaging several unbiased estimators decreases mean squared error, while the average still being unbiased. In practice, the empirical mean is often a nice estimator, and it is unbiased. Lastly, using unbiased estimator for data release seems to be more fair. In this work, we define the following general Gaussian noise mechanism. First, let us define the domain of data points to be K, a subset of the D-dimensional space, and our datasets contains endpoint from K. If there's some D by D matrix A, such that the domain K is contained by the ellipsoid A times D-dimensional unit ball up to translation, which is noted by this notation here, then outputting mx equal to mux plus z, where z is a univariate unbiased Gaussian noise with variance as specified here, to give us epsilon squared over 2 ZCDP. Also, this mechanism achieves the following upper bound and error. Here P is in 2 to infinity, and the LP trace is an extension of the standard trace. Here is an illustration of this mechanism. We first shift the domain to the unit ball, and on which we know how to add Gaussian noise. Simply add independent Gaussian noises. Then we shift the space back to the original domain, which is a post-processing. And the noise, after we shift back, have roughly the shape of the ellipsoid A times the unit ball. With the proper choice of parameters, this mechanism also works for epsilon delta dp, and we have the following upper bound on error. This comes from previous work, shows dCdp implies epsilon delta dp. It is also worth mentioning that our mechanism captures all mechanisms that adds correlated mean zero Gaussian noise to the mean, for example, factorization mechanism. This mechanism motivates the following problems to study. First, what is the best error achievable by a general Gaussian mechanism? Namely, there are a lot of matrices A that satisfies the containment requirement. Which one among them is the best in terms of minimizing the error of this mechanism? Another one is that, are Gaussian noise mechanisms indeed optimal among all unbiased private mean estimators? Can their error be improved on some nice datasets? To understand the optimum noise to add, we would like to understand the term square root raised p over 2 A times A transpose, which appeared in our previous upper bounds. So we define the gamma p function as follows. The infimum of this term among all A times the d-dimensional unit ball contains k to a translation. This is the key quantity we study and utilize in this work. And it turns out that this characterizes both lower and upper bound. Here are some nice properties of gamma p. Taking a convex hull does not change the function output. It is monotonic over containment up to translation. Scaling on k also scales the output by the same ratio. And surprisingly, it satisfies triangle inequality, where the sum here is the Minkowski sum. From these, we can see that gamma p really behaves like a norm, so not being one. In some sense, it can be considered as a way to measure the size of k by a bounding ellipsoid. Also, an optimal A can be computed, assuming we can maximize positive definite quadratic forms for k. With this notation defined, we now state our main optimality result for ZCDP. Any unbiased epsilon square over 2 ZCDP mechanism and any dataset X, we have a lower bound on error as stated below. Notice that this is not a worst case lower bound. It works for any dataset X. Recall the upper bound we have several slides earlier. They matches up to a log factor. Similarly, we have lower bounds on error for epsilon delta dp. For any constantly small epsilon and delta being a sufficiently lower order term, any unbiased epsilon delta dp mechanism M and n dataset X, there must be a neighboring dataset X prime, on which the error is lower bounded like gamma pk over epsilon n. Note that one cannot prove a lower bound and error for any dataset X. Since for any dataset X, there is an unbiased zero delta dp mechanism that has error 0 on X. Namely, this mechanism remember one dataset X and output the exact answer on it, while on any other datasets, it output exactly the same answer as if the input is still X with a very high probability to ensure privacy. And output some balancing output with the remaining probability so that it is unbiased. Now, we introduce the key ideas we used in our proofs. First, we prove the following lemma, which connects geometry with variances and covariance, allowing us to focus on the one-dimensional case. It says that if the width of k as shown in the figure here, any direction is bounded by the variance of the mechanism's output projected on that direction. Then k must be contained to a translation by the square root the covariance matrix of the mechanism output times the unit ball. This lemma, together with the following easy-to-prove inequality, which suggests that knowing the covariance of an unbiased mechanism, lower bound is error, tells us having a lower bound on variance in every direction is sufficient for constructing a d-dimensional lower bound and error. Now, we bound variance in every direction. We use the following key tool called the HCR bound. It says that for two random variables, u from distribution P and v from distribution Q, the standard deviation of v is at least the absolute difference between the mean of u and v divided by the square root of the chi-squared divergence of u and v. Here, we'll let Q be the distribution of Mx, and P be the distribution of Mx prime. We obtain the difference by cleverly selecting our neighboring datasets, and the divergence by the privacy assumption, and by the HCR bound, we are able to bound the variance by the width of the original space on each direction. Combining this and the previous law gives us the lower bound for ZCTP. To get the lower bound for epsilon delta dp, the same approach will still work, but extra efforts are needed. Here are some main modifications. We do a careful analysis on the distribution of the output of the mechanism. Due to the chi-square divergence can be infinite here because of the delta term. Then, for the reduction to one-dimensional cases, due to the impossibility of proving a lower bound and error for any dataset X, the original lemma would not work here. We used a modified argument here, but it only works for L2. To handle this, we introduced a reduction of LP error to L2 error. The last two here are based on properties of the gamma p function we proved. In summary, we proposed a general Gaussian mechanism and proved its strong optimality. And during the work, we defined and studied the key gamma function, which is very useful to characterize performance of Gaussian mechanisms. Additionally, in our paper, we also extend our result to local differential privacy and a setup where unbiased means distributionally unbiased. Here are the references we used in the slide. Thank you.